All right, dear students, here is a very important chapter called DC circuits, meaning direct current circuits. Now, in a direct current circuit, the current flows in the same direction and the magnitude never changes. That's why it's called a direct current. So it's basically constant magnitude, same direction. The other type of current that we will look at in a later chapter is called alternating current. That means the magnitude as well as the direction of the current changes continuously. Now, direct currents are supplied by batteries, while alternating currents are supplied by generators. You can also have generators produce a direct current, but usually direct currents are obtained from a battery, which is the source. There are two terms that you need to know in connection with a battery. Number one is the electromotive force. This is not at all a force. It's actually the maximum voltage that a battery can provide when it is not being used. So that means it's on the shelf and you would see something written on it. For example, it would say 1.5 volt. That means that's the maximum voltage it can provide when it is in open circuit. That means not being used. When the battery is being used, a current that flows through the external circuit, whether it's a light bulb or whatever the battery is powering, that same current must also flow through the battery. That's where the internal resistance of a battery comes into effect. Now, because of the internal resistance, when we use the battery, the terminal voltage that we get, which is the actual voltage available, the terminal voltage that we get from the battery, for example, to a light bulb, is going to be smaller than its EMF. So E is the EMF, I is the current that flows through the circuit, little r is the internal resistance. So you see by Ohm's law that current multiplied by internal resistance is the voltage that is lost. Now actually it's called the lost volt. And so the internal resistance leads to a loss of voltage. So the terminal voltage is always going to be less than the EMF. Now it is interesting to know that to make a battery last longer and also for it to produce a big current, its internal resistance has to be minimum. So in cell phones and in electric cars, the internal resistance is really low. Even in an automotive battery, a 12 volt battery, the internal resistance is like 0.01 ohm. Now compare that with the internal resistance of a cell like this, which would be about 1 ohm. So compare 1 ohm to 1/100th of an ohm. So here are some questions. Why does a battery's terminal voltage drop when current increases? Of course, it's from the formula. When the current increases, this part increases, so the terminal voltage decreases. And then a very simple worked out question. A 12 volt battery, so that's the EMF. The internal resistance given, it delivers 3 amperes. What is the what is the terminal voltage? This is what is lost. And so 12 minus that quantity gives 10.5 volt. So this is the voltage that is available to whatever is using that current from the battery. So here is the full circuit showing you how that circuit is completed. So you have the EMF of the battery, you have its internal resistance that is shown separately But you see that this box shows the battery. So this is not an external resistance. It's the internal resistance of the battery. But here, what you see here is an external resistance. So this might be the resistance of a light bulb or anything that is connected to the battery. So there's always internal resistance and external resistance. So now to find the current in the circuit, we have to consider both the external and the internal. And we will see later on that the total resistance is the sum of these two. So R plus R. And then I would be, let me try to write with this, I would be the EMF divided by R plus R. That's Ohm's law, right? Current is voltage by total resistance. So remember that. So there are some questions here. A battery has a cathode and an anode, and the anode is the negative terminal of the battery. So you see that the negative is shown with a shorter line and the positive is shown with a longer line. And you can also see that there are two cells connected together here, and that's when it's actually called a battery, see? So each one of them is a cell, an electric cell, and when you connect multiple cells like that, that's when you get a battery, okay? So here's another example. A battery provides 10 joules of energy to move 2 coulombs of charge. What is the EMF? So here we have to go back to the definition of voltage. Now, electric potential, we saw that it's work over charge, right? Work over charge. So work is energy. That's why it's energy over charge. So to find the EMF, you just divide the energy being used and the charge. So you get 5 volt. Simple thing. So once again, you have that. And when I usually ask students, what do you mean by the terminal voltage? And how do you measure voltage? We will see that it's measured using what's called a voltmeter. So a voltmeter. Suppose you connect a voltmeter here. Okay? How much is it going to read? Is it going to read the same as if you had connected a voltmeter across A and C? The answer is yes. Because electrically, this point C is the same as this point D. Because what do you have in between them? You only have a cable which has 0 resistance. Theoretically, okay? Practically, the resistance is negligible. So, electrically, E and A are the same point. So, you got to get this in your mind. You got to understand this. So, whether you connect something from D and E or from C and A, it's electrically the same thing because between C and D, there is no resistance. Same thing between A and E. Now, another thing that we can understand from this diagram is if you take a walk, if you move from A to E, this is important. When you move from A, you're moving from a lower potential, because it's a negative, to a higher potential. So the voltage is increasing. Now that's what is shown in the graph here. As you go from A to B, the voltage is increasing. You can see that. And increasing up to the EMF of the battery. Now there is another reason for that. The negative terminal is always considered to be at 0 voltage. I'm going to say that again. The negative terminal is taken to be at 0 voltage. So that's why the graph at A shows 0 voltage. And then when you get to B, the voltage, you can see B here, the voltage has increased up to whatever the EMF of the battery is. So if it is 12 volts, then it has gone from 0 to 12. And then when you go from B to C, the current flowing through this internal resistance, which is the battery, produces a potential drop. See the words potential drop. If the current is I and the internal resistance is R, then the drop is I times R. So that is what is shown here. When you go from B to C, there is a drop. You see that? That's the potential drop. And so now you end at the terminal voltage. See that? E minus IR. And then when you go from C to D, nothing happens to the voltage because there's no resistance there. So you have a flat curve there, so nothing, no drop. Again, when you go through the external resistance, there is going to be another drop in voltage. This time it's going to be I multiplied by capital R. Okay, there you go. And when you reach the point E, remember it's the same as point A, so the potential drops to 0. So I think you understood this. The diagram is very clear. You have to know this in order to apply what we're going to do in this chapter later called Kirchoff's laws. Okay, I hope that's clear. Now, I just wanted to put this in here, a battery charger. When you charge a battery, all you're doing is you are sending a current in the opposite direction to that which it would send when you use it. What do I mean? When you use this battery, currents are always going to flow from positive to negative, see? So that's the normal route, positive to negative. But when you're charging it, you're going to send a current exactly opposite through the battery. That's what you do when you charge it. So in that case, the chemical process is reversed, and then the battery is able to assimilate energy, and then you can use it for some more time. So that's what is shown here. Look at it. Look at the direction of the current. The current that is sent is now from negative to positive. Do you see that? Okay. Keep that in mind. All right, so the next topic is connecting resistors. You can connect resistors in series or in parallel, or you can have a mix of series and parallel. Now, when you connect resistors in series, you see that you connect them end to end, and therefore the total resistance increases. Now, this total resistance is also called equivalent resistance, as you can see here. The total resistance increases. It's actually going to be the sum of the resistors. But when you connect them in parallel, the total resistance actually decreases. It's going to be less than the smallest amongst them. So when you look at the formula, you'll understand that. If you have a 1 ohm connected with a 10 ohm, with a 50 ohm, and let's say 100 ohm, surely in this case, the equivalent resistance is going to be less than 1 ohm. It will be smaller than the smallest amongst them. So whenever we require the resistance to be really small, that's when we use a parallel connection. On the other hand, if you want the resistance to be higher, that's when you use a series connection. So, simple question here, if you connect all these three together, the total resistance is the sum of them, 20 ohms. Why does the resistance increase? Because the current must pass through each resistor, and each one is resisting it. And so there is a total opposition which is increasing because of the large number of resistors. Now, here is the same thing shown. So you have three resistors, R1, R2, and R3. And there is a particular current I flowing. If we could replace these three resistors with a single resistor, this one, which when connected to the same battery, if it would produce the same current as before, then this is called the equivalent resistance of these three. See that? Because it produces an equal effect current-wise. So by applying Ohm's law, we can clearly understand that the currents flowing through all three being the same, the potential drop here is IR1, here it's IR2, here it's IR3, and when you add all of them, you should get the voltage of the battery, assuming that there is no internal resistance in this case. That's why we get that formula. I'm not deriving the formula here, but you should have the conceptual understanding. Now, just like old Christmas lights, if you were to wire light bulbs in series, then we have a problem. Because if one light bulb fails, the entire string turns off. So with this, we understand that the home wiring circuit, or in school or in offices, wherever, it's not in series, because you want to individually turn on and off different light bulbs and different appliances. So it's a parallel connection at home and school. And in modern Christmas lights, it's again sometimes a combination, sometimes it's just a parallel connection. Because even if one light bulb fails, the others will still light up. Okay, here again, that's just in series. Okay, let's look at the parallel connection. Now, this is how we draw a circuit where two resistances are connected in parallel. Now, what happens is when the current reaches here, it splits into two parts, I1 and I2. And if R1 is bigger than R2, let's say R1 is 10 ohms and R2 is 1 ohm, then you can be sure that I2 is going to be bigger than I1. So that means the bigger chunk of the current, or the bigger part of the current, will flow through the smaller resistance. The bigger part of the current will always flow through the smaller resistance. And then they will come back and recombine, and then they will flow through the battery and the circuit will be completed. Okay. So here, this is the equivalent circuit where this resistance effectively replaces the other two. And in this particular case, the formula would be 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So if you add the reciprocals of the resistances, you would get the reciprocal of the equivalent resistance. Now be careful when you do this. I'm showing you an example, a very simple one. So let's say you got 6 ohms, 3 ohms and 2 ohms. And using this formula, you got to do 1 over 6 plus 1 over 3 plus 1 over 2. When you do the math, this is the lowest common multiple, so you get 6 over 6, which is 1. And so when you flip this, it's also 1. But let's say that in another case, you got 1 over R is equal to 5. Let's say that. Many students make a mistake here. They forget that if 1 over R is 5, then R is 1 over 5. So please don't forget that. An easy way to check it out is, remember what I told you, it should be smaller than the smallest resistance. In this case, the smallest resistance is 2 ohms. And see, it turned out to be 1 ohm, which is smaller than the smallest. So that is resistors combined in series and in parallel. Now this is a very interesting circuit shown in the textbook. We're going to try to see how we can simplify this circuit. So we're trying to find the equivalent resistance of all of these. Now what you got to remember is to start from start as far away as possible from the battery, which means first you got to look at this and say, how is this connected to R3? Is the same current flowing through these two? Of course, because there is no other path for the current to flow. Now, since the currents are the same through R3 and R4, that's why we know they are connected in series. Therefore, that's what we do first. So as you can see here, R3 and R4, you add them because they are in series. That's 10 ohms. So we draw the next circuit with 10 ohms. See that? So we've replaced these two with 10 ohms. So that's why it's called R equivalent of 3 and 4. That's 10 ohms. Next question is, when a current reaches this junction, would it not split into two? Yes, it would. One part would go through R2, the other part would go through R sub 3, 4. So is it the same current flowing through these two? Not necessarily. In this case, it would be the same, I'm telling you, because the values of the resistances are equal. But generally, the currents will not be the same. That's why we know that these two are in parallel. So simplify this using this formula. And then you understand that it's going to be 5 ohms. The equivalent of these two is 5 ohms. All right, that's another point to be noted. If you have two equal resistances connected in parallel, then the equivalent resistance is always going to be half of one of them. Always. That's why these two are now replaced by 5 ohms. And so we now have this circuit. So we still have the 7 ohms. And then we have this equivalent of 2, 3, and 4 as 5 ohms. Now, how are these two connected? Of course, they're connected in series, because the same current has to flow through both. So what do? We add them. So it's 7 plus 5, 12 ohms. So finally, we end up with this circuit. So can you tell me what the current through the battery is? Yes, it's 2 ampere by Ohm's law. 24 divided by 12. Okay, so can we go back and can you tell me what the current would be that flows through the 7 ohm? Yeah, 2 ampere. It should be the same through both of these. And so on and so forth. So this is how we manually simplify complicated electrical circuits. But this method cannot be applied in very complicated circuits. No, like if you look at the circuit of a radio or a television, it's impossible to use this method to simplify the circuit. And that's why we have to use what's called Kirchoff's laws. Kirchoff is a German scientist who gives us these laws. And this is very important. There are so many network theorems. That's what they're called. Network theorems in electricity. And this is the most basic one. So in the first of Kirchoff's rule, actually it's called the junction rule. Kirchoff's junction rule, because you're looking at an electrical junction. So at any electrical junction, which is a part of a big electrical circuit, there will be some currents that are coming in and there will be some currents that are going out. As you can see, I5 and I4 coming in, I6 is going out from the junction or going away from the junction. Now, according to the junction rule, the total current coming in should be equal to the total current going out. That's what you see here. So you add all the currents coming in and set them equal to the currents going out. Now, what is the significance of the junction rule? It shows us that there is no stagnation of charge at a junction. Whatever comes in goes out. Nothing settles there. So that's the consequence. Or in other words, it's a consequence of the conservation of charge. Charge coming in is equal to charge going out. That means charge is not created or destroyed. Okay? Again, this junction rule is used for analyzing complex networks in electronics. And I've already told you this. This is the importance. Charge cannot accumulate at a node. Node is another word for junction. And here is a simple problem. You should be able to figure that out. Okay. If the total coming in is 7 ampere and whatever is going out is 2 plus Ix, then what is Ix? I sub x is 5, of course. Okay. Let's go to the second rule called the loop rule. Now, a loop must always be closed. So if we start from A, B, C, D, A, that's the loop which is closed. You can see that's the electrical loop. Sometimes it's called a mesh. And we've already set the ideas to understand this. According to the loop rule, which is also called the voltage law, if you add up all the potential differences or the voltage, you must get 0. So the algebraic sum, see, look at this word. Algebraic means you have to consider the sign, whether it's positive or negative. If you consider the positive and negative of all the voltages around any closed loop, you would get 0. I'm going to explain that. But understand that this is a consequence of the conservation of energy. So the first law is a consequence of conservation of charge. The loop rule is a consequence of the conservation of energy. Again, it's used to solve for unknown currents and voltages in multi-loop circuits, and surely this is going to be a question for you on the exam where you have to apply these two rules and solve for the current. You will see that in the problem set. Now, why must the total voltage be 0? Because the energy gained from batteries must be dropped off, means used up by resistors and whatever other elements are in the circuit. So this is a very simple one. If you have 2 resistors and you have this battery of 12 volts, what's the current? We actually did it, it's 2 ampere. Okay, so let me explain the loop rule with this diagram which you have seen before. Now when you start moving from A to B, the voltage goes up. So negative is taken as 0. So here you would put plus 12 because it's going from 0 to plus 12. And then when you go across the resistance 1, you would put it as whatever is the current multiplied by 1. That's the voltage, right? Would that be a positive or a negative? It would be a negative because the potential is dropping. Another way to understand it is this. This end of the resistance is going to be positive because it's connected to the positive of the battery, which means this end is negative. So now when you go from here to here, you're going from positive to negative. That's why it's dropping. How much is it dropping? Whatever the current is multiplied by the resistance. So if the current is I, it's going to be I times R1. Same thing here. It's again going to drop because this end is positive, this end is negative. So it's going to drop by I times 2. Again, it's going to drop by I times 3. Same reason, because this end is negative, being connected to the negative of the battery. See that? So that's shown here in the diagram. And because we know that the current is 2 ampere, if this is 1 ohm, so it's 2 volt here, right? 2 times 2, 4 volt here and 6 volt here. That's what is shown here. So you go to 12 volt and then you see the spot. This spot is where the connection cable is. Nothing happens. And then it drops off from 12 to 10. Why? Because the voltage drop here is 2. The current is 2 ampere multiplied by 1, right? I hope you're getting it. So it drops by 2. And then when you go from here to here, nothing happens. So the flat one. And then again it drops by 4. So now it goes from 10 to 6. Why does it drop by 4? Because the current is 2 ampere, 2 times 2 is 4. Okay. And then again here that's flat, and then here is going to drop by 6. So you're already at 6 here, and you drop from 6 to 0. So that is the application of the loop rule. So we're going to see how we're going to use this. We have to apply the junction rule and the loop rule, set up equations. All right, these are called simultaneous equations, linear equations, and I'm sure you know how to solve them. Okay? One easy method of solving simultaneous equations is to use matrices. So if you know that, it will become even easier. So electrical engineers use these rules in analyzing microprocessor circuits, automotive systems, and power distribution grids. Why can't we use Ohm's law alone? Because Ohm's law is applicable only to individual elements. But Kirchoff's rules, here you see it, Kirchoff's rule accounts for the entire network. We take the whole loop, or we consider the whole, the junction. So it's not applied to individual elements. So here is a very simple example that's worked out. And I've drawn it. It's a 2-loop circuit. Loop 1 has a 12-volt battery and resistors 2 ohms and 4 ohms. So that's loop 1, 12-volt battery, and you have 2 ohms and 4 ohms. So this is loop 1. And then loop 2 shares R2. So, yep. And has R3, 6 ohms with no battery. So there's no battery in loop 2. Find the currents I1 and I2. Now, first of all, before we begin solving it, you have to name the currents. So let's assume that this current is I1. You can call it anything. But if we call this as I1, when I1 reaches here, it's going to split into 2. So let's call this part I2. Excuse me. So the current that flows through this part is I2. Now we need not call this I3. We can be smart to call this I1 minus I2. Because if you call it I3, then you're going to increase the number of variables. Okay? Is that clear? Because one thing is sure, that when you add I2 with this, you must get I1. Because whatever is the current coming in, which is I1, must be equal to the total going out, right? So that's why we have called this I1, called this I2. This must be I1 minus I2. Simple. And then you apply Kirchoff's loop rule to loop 1. What are you going to get? If we go from here, you're going to get plus 12 minus 2I1, right? You know why it's minus, correct? Because the potential is dropping. So 12 minus 2I1, and then again you're going in the same direction as the current, so the potential is going to drop. How much? 4 times I1 minus I2. So that's why it's there, is equal to 0. So we got one equation from loop 1. Now you can distribute this, rearrange, collect the I1 terms, and you would get this equation. Or in other words, 6I1 minus 4I2 is 12, right? Yeah, I've just rearranged those, and that's when you get that equation. That's called equation number 1. Okay. Now, can you apply the loop rule to loop 2 without looking at it? You should be able to. You can start from here, and you go this way. When you go this way, since you're going in the direction of the current, the potential is going to drop. So you would go 6 times I2, right? 6I2, and then continue. You're coming down, nothing here, and now you're going up against the current. When you go against the current, the potential is not going to drop, but it's going to increase because this end is positive. This end of R2 is positive. Why is it positive? Because it's connected to this. So here you would go 4 times I1 minus I2, but you would do plus 4 times I1 minus I2, not minus. So that's in loop 2. Let's look at it. So you can go 6I2, which is the same thing that's basically written here. So I said 6I2 plus, isn't that what I said? Plus 4 times I1 minus I2 is equal to what? Is equal to 0, because there is no battery in the circuit. Okay? Okay, so whatever I was telling you was correct, but I noticed that I had put a negative here, so I changed it to positive. And I told you the reason, right? This is, you're going in the direction of the current, it's negative, and then you're going opposite to the current, because the current is coming down, that's why it's positive. So that was a mistake. And so when you do that, you will end up with this equation. I've written it down, you can see that. Distributed the terms here, collected these two as negative 10I2 plus 4I1, so you get your second equation. And solving the first and the second by substitution, elimination, whatever method, you can get the currents as 2 and 0.8. 2 ampere and 0.8. So that's a simple example of the application of Kirchoff's laws. And again, it's going to be on the exam, so you got to know how to solve this. In this circuit, there are only 3 resistors, but there could be many more, and you should be able to apply it. All right, so those are Kirchoff's laws and how you apply. So this is again exactly what I explained here. If you're going in the direction of the current, so if the direction of travel is in the direction of the current, then you put negative I times R. But if you're moving opposite to the current, then you put positive IR, okay? So that's shown here. But in the case of a battery, if you're going in this direction, you're going from negative to positive, so you put positive. But if you're going this direction, you're going from positive to negative, so put negative. I hope it's not confusing. If you are paying attention, it's not confusing. I've explained it using the diagram and then using the logic here, so you should know that. Right, so there is another circuit for you to try to solve. It's almost the same as before, except that there are batteries now in both parts, okay? So you should be able to apply that and try to solve the question there. Now, did you know that all these gauges that you see in your car are basically voltmeters? They are meters, of course, but they are voltmeters showing the voltage. Now, a voltmeter is used to measure voltage. And the most important thing is for you to remember that a voltmeter must be connected in parallel, because it should be connected across the 2 points where you want the voltage. And voltmeters have very high resistance because you do not want any current to flow through the voltmeter. Because imagine that you're using an instrument to measure something, and if you plug in that instrument, if the whole current changes or the voltage changes, then you're going to measure the altered voltage, right? We don't want that to happen. So voltmeters have very high internal resistance, conceptually very important. All right, why should it be connected in parallel? Because you're trying to measure the potential difference directly across. Like shown in this example, you can see the 3 voltmeters. First one is measuring the voltage across the battery terminal voltage. And here we have this one connected across R1, and this is connected across R2. So That's how a voltmeter is connected. Also, remember, the positive terminal of the voltmeter should face the positive of the battery. See that? And the negative should face the negative of the battery. Always. If you put it reverse, then the voltmeter is gone. It won't give any reading because the pointer will try to go in the opposite direction. And if you do that for some time, then you destroy the voltmeter. So keep that. So voltmeters are always connected in parallel. They have very high internal resistance, and their polarity, meaning the positive and negative, should be lined up with the positive and negative of the source. Okay, so that's what is shown here. Oh no, here we're trying to measure the current. When you measure the current, you use what's called an ammeter. So when you connect an ammeter, you want that same current to flow through it. So if you're trying to measure the current through R1, don't you want that same current to flow through the meter? Yes. That's why it should be connected in series. So an ammeter is always connected in series. You can see 3 of them. This one is going to measure the current that flows through this part. Second one will measure this current I1. The third one will measure this current I2. And it's always connected in series, meaning this meter is connected in series with this. This one is connected in series with this. Okay. And an ammeter is a very low resistance instrument. Again, it has a very low internal resistance. The reason is we don't want it to alter the current in the circuit. Because if this was a high resistance instrument, then what's going to happen when you put it in there? That's going to increase the resistance to a very large value, and the current is going to become very small. So that's why you want this to have like 0.0001 ohm. Okay? All right, so that's what is mentioned here, and here's an example. An ammeter with 0.01 ohms internal resistance, see, very small, is connected in series with a 5 ohm resistor and 10 volt source. What's the current? What do you do first? You have to add these two because they are in series. So you get 5.01 ohm. Then apply Ohm's law. 10 divided by that, because according to Ohm's law, I is equal to voltage by resistance. Is it not? Total resistance in this case, or equivalent resistance, whatever you call it, and you get 1.996 ampere. So that means the introduction of the ammeter only changed the current from 2 ampere to 1.996. Notice that? Because if this instrument was not there, then the current would have been 2 ampere, 10 divided by 5. Now, there is a third type of instrument called an ohm meter. We won't go into details about this. But remember that, well, of course, the name shows that it's used to measure electrical resistance, ohm meter, and it uses Ohm's law. That means if you want to measure the resistance of something, you have to send a current through it. And by measuring the voltage applied and the current flowing, you can calculate the resistance. That's what the meter does. It just calculates it for you. So whenever you use an ohm meter, it has a battery with it. And so it is sending a current through whatever you want to measure. And then by measuring the current, it's giving you the value of the resistance. Now remember that the voltmeter, the ammeter, and the ohm meter could be combined into one instrument. It's called a multimeter. You're going to see that. Or some of you would have already used it. You can measure anything with just one meter. You just flip a switch and it becomes a voltmeter, and then an ammeter or an ohm meter, and even more. And it's a very useful instrument for troubleshooting, to test resistors, wires, and continuity in circuits to see if there is any break in the circuit. But an important thing is before you use an ohm meter, it should be unplugged. Not the ohm meter, I mean the circuit should be unplugged. So if you're trying to measure the resistance in a live circuit, it's not going to work. Because you don't want any other current to flow through the resistance except the current sent by the ohm meter, because it's going to base its decision on the current that it sends. Okay. And also an active circuit can interfere with the meter's internal voltage, resulting in inaccurate readings. That's what I told you just now. So here is a simple example. An ohm meter applies 3 volts, measures 0.5 ampere. What's the resistance? Of course, 6 ohms. Come on. We're coming to the last part of this chapter, a very important part. It's called a resistance-capacitance circuit. So this is where you have a resistance combined with a capacitance. Now this type of a circuit is used in so many places. The best example I can give you is in the wipers. You can adjust the timing of the wipers in a car. Windshield wiper, I mean. So you're using an RC circuit. So anywhere you need any kind of timing, you are using resistance and capacitance connected together in series. So in a clock, this is the basic idea of measuring time. Because this, you're going to see, when we look at the equations, you're going to see that it's a time-based circuit. So let's get into it. Now, let me explain the circuit. So you have a source here, and you have a flip switch. So that means this switch can be put in contact with either A or B. If you flip the switch and put it in contact with A, as shown here, then a current begins to flow, and that current flowing through is going to charge the capacitor. Now the capacitor gets charged to a maximum. And once it gets charged, if you flip the switch from position A to B like this, then the capacitor is going to discharge through the resistance. And in that case, it's going to send a current exactly opposite to when it was being charged. The reason is because the top plate is positive and the bottom plate is negative. Currents always flow from positive to negative. So this is how you charge a capacitor. This is you're discharging the capacitor. One of the other important quantities in this circuit is the voltage of the battery, which is E. And the other two are the resistance and the capacitance values. That's all we need. We're going to find out an equation for charging capacitor. I'm not deriving it here, but you have to know that this is going to be an exponential equation. Here it is, very important equation here. The charge on the capacitor, this is for charging. When you charge it, the charge on the capacitor at any time t is given by C times E. Now C times E, you may remember, is the maximum charge. Okay, because from the chapter on capacitors, we know that Q is C times E. So that's the maximum charge on the capacitor. So CE, and then 1 minus e raised to minus t over RC. Okay, so that's why it's an exponential one. And likewise, the voltage across the capacitor has a similar formula, only that it's simpler. If you're talking about voltage, then you just put the EMF of the battery and the same function. 1 minus e raised to minus t by RC, okay. E is the battery voltage, C is the capacitance, R is the resistance, and R times C is actually called the time constant. Note that down. So if you multiply the units of R and C, if you break it down, like it's ohm and farad, right? You break down ohm and farad, you're going to end up with seconds. Isn't that interesting? That's why it's called the time constant. It is a time. It should be a time. Because if you divide time by something, and you know that exponential should just be a number, then these two should have the same unit. Okay. Capacitor charging is used in flash photography. So where you see the flash of a camera, that's actually a capacitor charging and discharging. It's when it discharges that the light bulb flashes. And power supplies, of course, all power supplies have capacitors, and then defibrillators are also capacitors, larger capacitors. Why doesn't the capacitor instantly charge to the battery voltage? We do not want it to. So just think, if you connect a capacitor directly to a battery without a resistance, you're going to blow up the capacitor. It's gone. Because you're trying to give it a charge instantaneously and it can't take it, it can't handle it. That's why usually the resistance used is big. It'll be like 1 mega ohm or 2 mega ohms of that order, because you want the capacitor to assimilate or accumulate charge slowly. Now when I say slowly, it could be just 1 or 2 seconds, but in the electrical world, that's slow. Okay, we are trying to slow down the charging of a capacitor. So here is an example. A 10 microfarad capacitor, so that's the C value, is charged through a 1 kilo ohm. I said mega ohm, at least they're using 1 kilo ohm here from a 12 volt battery. What's the voltage? After 2 time constants. Oh, so we know time constant is R times C. And in this case, if you multiply 10 microfarad with 1 kilo ohm, okay, kilo ohm is 1000 ohms. And 10 times 10 to the negative 6 is 10 microfarad changed into farad. Then you get 0.01 second. So that's the time constant. So 2 times that is the, what's the voltage across the capacitor after 2 time constants? So let's plug it into the formula, the voltage formula. Voltage at any time t is maximum voltage, which is that of the battery, 12 into 1 minus e raised to, minus 2. Why? Because you're going to get T by RC, isn't it? T by RC. And because we said that this should be 2 time constants, you're going to get 2 over 1, that's 2. And when you do the math, you get 10.38 volt. So notice that after 0.02 seconds, the voltage on the capacitor has already increased to 10.38. It's very close to the maximum. Notice? That's what happens if you use a 1 kilo ohm resistor. If you had used a 1 mega ohm, you would have slowed it down even more, which means you're protecting the capacitor. Okay. So these graphs show how the charge builds on the capacitor. You can see that this is the nature of an exponential graph. It approaches max, which is C times E, but never touches it. Okay. Once again, this is the voltage increasing similarly. But while that is the charge across a capacitor and the voltage, now for the resistor, it's going to be exactly opposite, because when the capacitor gets more charge, the current is going to slow down and approaches 0. Because when the capacitor, just listen carefully, when the capacitor gets more and more charge, it's fighting the battery. So the battery is now finding it more and more difficult to send a current. And when the capacitor gets equal voltage as the battery, there's no more current. Okay, so that's why the graphs are opposite across a resistor. Now when it comes to discharge, when you're discharging it, of course you start from maximum, and then the charge across the capacitor is going to go to 0 because it's discharging. Same thing with the voltage. But for a resistor, the current increases. So at the beginning it's 0 and then it increases. But you should notice that the voltage across the resistor has the same fall as that of the capacitor, because the voltage is given by the capacitor, and that's discharging. So there's no more potential, there's no more voltage. So it decreases both across the capacitor and the resistor. Look at the equations for discharge. It's not the same. You know what is missing? The 1 minus is missing. You see, the 1 minus e raised to is gone. You don't have 1 now. It's charge is this. That's the maximum charge, and that's the maximum voltage, e raised to minus t by RC. Okay. So here it's called the initial charge and initial voltage, which is the maximum, of course. Once again, the time constant is the same. Discharge processes are critical in timing circuits and power down operations in electronics. Why doesn't the voltage drop to zero instantly? Because the resistor is limiting the rate of discharge. A simple problem worked out here. A 20 microfarad capacitor discharges through a 500 ohm resistor. So you given the values of the capacitor and the resistor, should be able to find the time constant. All right, same thing. What's the voltage after one time constant? Okay. So plug it into the formula and you get 3.68 volt. After 0.01 second, the voltage has dropped from 10 to 3.68 volt. So it's not that slow. Where are RC circuits used? I gave you some, but they're also used in what's called filter circuits. They're used in a variety of real-world applications due to their time-dependent behavior. They function as low-pass and high-pass filters, so you can filter out certain frequencies. They are also used as timing elements in electronics. I told you they're used as energy storage elements in flash cameras and defibrillators. Okay, practical applications. Why are RC circuits used as filters? Because their voltage varies with frequency. That means you can block specific frequency ranges. This formula is something we're going to derive when we do alternating currents, but just introducing it here. An RC low-pass filter has these values. What's the cutoff frequency? Just remember, it's not going to be on this exam, but we're going to see how we get this formula and we're going to use it. The cutoff frequency is 1 over 2 pi RC. So plug it into that, and that's the cutoff frequency, okay? All right, so now read these parts, basic concepts in house wiring. I already told you that circuits at home are wired in parallel. Two reasons: we want to independently switch on and off the different appliances. Not only that, in parallel, all appliances get the same voltage because they are all individually wired to the source. And at home, every appliance, we have to give it 120 volt. And then we know that at home, for safety purposes, we have circuit breakers, we have fuses, we have what is called GFCI, ground fault circuit interrupter, okay, GFCI, where at wet locations that's what you use. Wherever you have to set and reset, that's what. So all these are safety devices. Now, color coding, I'm not going to ask you all this on the exam, but it's important for you to know that the hot wire or the live wire is black. The white is neutral. And the green is the ground. I'm talking about a 3-phase connection, a 3-pin plug, if you may, that you plug into the socket. There are 3 wires. There's one live wire, there is a neutral, and green. All this will make more sense as we go on, okay? Why should home outlets be wired in parallel? Yeah, I told you they should all get the same full voltage and also work independently of the others. 120 volt circuit has 3 appliances drawing these currents. What's the total current? Come on now, add it up. That's it. Because the currents add up. All right. So that's showing a short circuit here. This is if there is a contact where there should not be any contact, what's going to happen is that's when it's called a short circuit, and the current, instead of flowing through the higher resistance path, now takes a shorter path this way. That means the resistance being low, the current is going to be really high, and it'll produce a lot of heat, and there's chance of fire. So short circuits are dangerous. That's why we have fuses here. So this could be a fuse, and because of that high current flowing through the fuse in the plug, it melts, because it has a low melting point, it melts. Okay. And read about all the hazards there. You're not going to be asked about those on the exam, but it's important for you to know. Effects of electrical shock. Okay, current magnitude. The maximum that the human body can take is 5 milliampere. 5 milliampere. Beyond that, it'll cause pain. More than 100 milliampere, gone. It's fatal. And then it depends on the path that the current takes through the body. If it's across the heart or brain, that's most dangerous. It also depends on the duration of the flow of current and the resistance of the skin and the clothing, And again, AC is much more dangerous than DC at the same voltage. And you will see the reason why. So if you get an electric shock from a battery, which is rare, and you have the same electric shock from AC at the same voltage, AC is more dangerous. And again, you're going to understand why. There's a lot more to be done here. Okay. A person has a body resistance of 1000 ohms, touches a 120 volt wire. What's the current? Wow. Gone. Now these are typical values. So if you touch a 120 volt wire and we have a typical resistance of 1000 ohms, that's going to produce a current more than, remember, 100 milliampere. This is 120 milliampere, right? So that's why it's fatal. Okay, so fuses and circuit breakers. You all know this. A circuit breaker is an automatic switch that trips open and you can reset it. I talked about the fuse. Here is a wiring circuit showing you the colors that I told you about. Just take a look at this. And that brings us to the end of this chapter, because I wanted to finish in at least 1 hour. Thank you. I hope you understood all the concepts in this chapter. This is a very important chapter. I'm going to carry majority of questions on the next exam. So even after taking the quiz, read the textbook or look through this and try to understand it. Okay? I will see you on the next one. Thank you.